Hi, everybody. It is week 9 in our chemistry class, and this week it is all about writing and balancing chemical reactions. Here's the story so far. We've been talking about how elements react to form compounds. We've talked about those ionic and those covalent bonds. And we've talked about how moles and Avogadro's numbers can be used to determine how much of a reactant or a product are involved in a chemical reaction. We've looked at groups and families on the periodic table, and we've looked at who reacts with what. But now we are going to talk this time about how to actually write a chemical equation, how to write those chemical reactions out, because it's a shorthand. There's a lot of information that is hidden in a chemical reaction if you know what to look for. So let's look at all those detailed pieces. First off, in every chemical equation, there's a general format, and the format goes like this. On the left-hand side are the reactants. Those are the things that are being reacted. On the right-hand side are the products. This is what is being produced by whatever the chemical reaction is. There is always an arrow, and the arrow can be read as yields. The yield is the production. When you talk about a field yields so much corn or yields so many soybeans, that is the product, what is being produced. So if I look at this chemical reaction down here, we could read it as sulfur dioxide gas reacts with oxygen gas to yield sulfur trioxide gas. These are my reactants, and these are my products. So it's pretty simple to keep straight. Things that are doing the reacting are on the left. The products, the production of that chemical reaction, are on the right. One of the other shorthands that are in every chemical reaction is the state of matter: solid, liquid, gas, or aqueous, dissolved in water. If something is a gas, we put a lowercase g in parentheses next to it, a liquid, lowercase l, a solid, lowercase s, and aqueous, lowercase aq. So, for example, if I have ice here, some plain old water ice cubes, and I wanted to indicate that, I would say H2O solid. Nice lower subscript solid written behind the H2O. If I wanted to indicate liquid water, I would go H2O liquid, a subscript of a little l. And H2O water vapor, I would go H2O gas, lowercase g. So with a simple addition of that state of matter indicating subscript behind the product, I can say if it's a solid, a liquid, or a gas, and that tells me an awful lot about what form the chemical is in. Now let's talk a little more about aqueous. Aqua is the Latin word for water, and we use that abbreviation AQ to indicate that something has been dissolved in water. And again, it is a wonderful shorthand way in a chemical reaction to explain something without having to go into an awful lot of detail. This is the basic chemical formula for sugar, common sucrose, table sugar, C12H22O11. If I want to indicate the kind of table sugar you might have in a sugar bowl on your kitchen table, I would say C12H22O11 with a little s for solid. Now, you may have noticed on the previous page, besides the S, I had a little C. Now, you might have said, Mary, what's the C for? An older way of indicating solid was to use a C to stand for a crystalline compound. And it's not as common as it used to be, but because of the fact that when you're dealing with an ionic compound, the solids are going to have a definitive crystalline structure. I have seen in some textbooks, and some older chemists will use a C to indicate crystal instead of solid. So I just want you aware of that symbolism. I will tend to stick to S for solid. If I want to indicate that I have a sugar-water mixture, I'm going to say C12H22O11 aqueous. Now, notice I'm not saying what percentage water, I'm not saying how diluted the solution is, I'm just saying I've got a sugar-water solution. If I want to say salt crystals, I'm going to say NaCl solid. And this is a saline solution that might be used to give a patient a nice IV of some liquids. That's just going to be NaCl aqueous. Again, the concentration of the solution is not indicated, but by that simple subscript, I can say a lot in a very short amount of space, and that's what we try and do in a chemical reaction. One of the other things that is often included in a chemical reaction, but it is not required, it's sort of up to the writer, it's up to the author of the reaction, if they include the conditions of the reaction. Now, the conditions of the reaction is the energy that must be added to make the reaction occur, and that is also called the activation energy. We're going to spend more time on activation energy in future lectures, but for the moment, we're talking about the little kick in the pants that you've got to give the molecules in order to make them bond with each other. This reaction here, CH12, this is methane. If you have a gas stove, odds are you have methane that comes out of your gas stove. O2, of course, is elemental oxygen that is in the atmosphere. And if you just open up the valves on your gas stove, it's not going to spontaneously combust. You have to hit it with some sort of a striker. Usually in a gas stove, there's an internal striker that will ignite the methane with the oxygen. And when those two combust, the products are carbon dioxide and water vapor. Now, you have to add something to make this happen, and that condition of reaction can be added in the equation, but it's not put in the equation, it's often put above the yield sign. And if you need to kick the reaction, activate the reaction with heat, very often it is done with a little triangle, and the triangle means the addition of heat. Now, some chemical reactions are activated by light. Hydrogen peroxide will decompose very often in the presence of light, and that's one of the reasons why it is typically stored in a brown or an opaque bottle, because we don't want light getting to it and decomposing it, then it will be useless. But if we have hydrogen peroxide liquid, it can be accelerated and decomposed by the presence of light. And if I chose to include that information, I'd put it above the yield sign, and that would decompose into liquid water and gaseous oxygen. If you use hydrogen peroxide as a disinfectant, the oxygen is what creates the bubbles, and the oxygen bubbles are what actually does the disinfecting, because oxygen is a wonderful disinfectant. It is a group 16 element, and those non-metal group 16s are pretty good disinfectants. Another condition of reaction or activation energy is sometimes electricity. And a wonderful example of this is the electrolysis of water. If you take normal water, all by itself, water does not decompose. But if you pass electricity through some normal water, you can break it into hydrogen gas plus oxygen gas. And that can give you these two gases. Well, hydrogen gas has been used and is being used as a fuel to propel everything from semi-trucks to automobiles. Where is this being done? Well, it's being done in places where electricity can be made very, very cheaply. And one of the places that is being done is in Iceland. Iceland has lots and lots of volcanoes. The heat from the volcanoes is being used to make electricity. The electricity is being used to break apart water molecules, and then the hydrogen gas fuels the cars. why are they going through this process? Because the volcanic heat is not terribly good at running your automobile, so they have to transform it into another form of energy that is more useful for running a vehicle. When you're writing a chemical reaction, if the element you are using is a natural diatomic, if you remember those dirty seven, you remember hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, those elements always occur as two identical atoms bonded together. They must be written in their diatomic form if they're going to be in their pure form in a chemical reaction. So, for example, hydrogen peroxide, when it decomposes into water and oxygen, you do not write O, you write O2. When methane burns with oxygen, you don't write O, you write O2. When phosphorus reacts with chlorine, if it's reacting with pure chlorine, it's always Cl2, chlorine gas. Now, chlorine is not always Cl2 because when it's in a compound, it can be in a different organizational structure. Oxygen is always not a 2Z. Nitrogen is not always a 2Z, but when it's by itself, it has to be in this diatomic structure if it's one of those dirty seven. If you're reading a chemical reaction or engaged in a chemical reaction and something is burning, burn or rust means to react with oxygen. So if one of the things we're going to do in the next talk is we're going to translate from English into chemistry. And if it says that something burns, that means reacts with oxygen. If something oxidizes or rusts, that means reacts with oxygen. And so you have to learn some of this vocabulary in order to do the next step, which is translating from English into a chemical reaction. And last but not least, when we start using a lot of acids and bases typically are going to be in an aqueous solution. Hydrochloric acid, sulfuric acid, ammonia, plain old ordinary cleaning ammonia that many of you have around your home. These are water solutions. And the way we indicate chemically in a reaction that these are aqueous solutions is we include that AQ. Most of the acids and bases that we're going to work with in this class are going to be watery solutions or aqueous solutions. The exceptions that you're going to encounter when you take organic chemistry, biochemistry, you will encounter some fatty acids. That's not something we are going to deal with in this course, but our acids are typically going to be watery solutions. So that will do us for this time. Next time, my friends, we're going to come back and we're going to start writing some chemical reactions. See you then.